Hi everyone. So today we'll be describing uh, about the International Math Olympiad, that is the IMO. So IMO is a very prestigious mathematics forum for young mathematicians all across the globe. Basically, it is a forum for undergraduate uh, geniuses in mathematics who are very passionate about problem solving in mathematics to showcase their talent and get globally recognized, right? So in this IMO, every country actually nominates its team, and there is a list of teams that compete for the top position in it. They are given a rigorous 6-month training by the top mathematicians in the world, and they prepare themselves for the final. Right? Final basically has 7 questions, out of which 2 questions will always be very tough. Right? So it has been a what you tell. It has been for quite a long time. This Iowa has been a prestigious examination for quite a long time. So in this history of this IMO, one particular question is notoriously tough. So rather than me describing how tough it is, let us ask. This is the Google AI mode. Let us ask Google what is the toughest question in the IMO. Let's say, what does Google has to tell? Okay, so here Google has described the while hardest is subject to, obviously it is. Problem 6 from the 1988 IMO is widely known as the toughest problem. Okay, that is what Google has to tell. So why is it tough? So if you look at it, there was an Australian mathematics committee which couldn't solve this problem in 6 hours, right? This is not the members; it is actually the world-class mathematicians from Australia who are actually in the panel, in the question making panel. So they'll actually attempt the question first. So they were not able to solve it in 6 hours. So that was the level of difficulty that this question had. Okay. So another just, I mean, this question actually, no, it actually brought new techniques into the mathematics forum. That is the Vietnam jumping and a lot of those things. And one more way to, I think everybody is very much aware of Terence Tao. So the Terence Tao is one of the brightest minds who are alive today. I think he has a YouTube videos. Most probably all of you might have seen it, his YouTube videos. So he has got only 1 point out of 7 on this problem. So you can imagine how difficult this problem was, right? I mean, at that time, Terence Tao was just 13 years old. That is to be noted. But yeah, but still, right? This was actually such a difficult question. Now let's dig deep into the question. See, you have a lot of these. There are a lot of. I think this is one of the solutions that is presented to this question. A lot of people who give very good detailed solutions for this problem. So my intent of this video is not to give a solution to this, to give a very simple solution which can, what you tell, which can induce creative thinking in the viewers, right? That is the main target behind me putting this video here, right? So the many often we can relate mathematics to creative daily concepts, right? Creative imaginative concepts. That's how I call it. It becomes very tough problems becomes very easy to solve, right? So that is what I'm going to showcase here. Now let's dig deep into this question, right? Let's see, first let's understand this question. Let a and b be positive integers such that ab plus 1 divides a squared plus b squared. So the first line means that a square, you have two integers which are positive integers, and a square plus b square is divisible by ab plus 1, right? That's all. A square plus b square, two integers, a square plus b square is divisible by ab plus 1. You have found such two integers. Then if they divide, if let's say a plus ab plus 1 divides a square plus b, a square plus b square, then that quotient is a perfect square, should be a perfect square, right? Should be the square of a number, right? So that is what this question. Just prove that that quotient will be a perfect, I mean, the square of an integer, right? So this is what this entire question is about, right? Very humble question. That let's see how we can actually solve this. Okay. So now, so first things first, we'll just we have a mathematical question. So best thing to do is first just write down the problem. A squared plus b squared is divisible by ab plus 1. Okay. If it is divisible, this may not be divisible, but if it is divisible, then it has to be a square of an integer. This is what we are asked to prove. Now, I want you guys to just think of an imaginative, let's say, compare it to a real world scenario or something like that, right? Suppose you have a, let's take geometry for our reference now. You have a square A, and you have another square B, B. Okay. And you need to divide it by, let's say, another rectangle of side A and here B plus, let's say, another block of 1, 1. Okay. So it's as simple as representing this question, right? Suppose you have, let's say, A square people are standing in A rows and A columns, right? Then this they will form basically, then total number of people will actually form some sort of like a square, right? Same thing with B square. B square people are standing in, let's say, B rows and B columns. Same way, they'll also form a square, right? So now, actually, the question is, if the numerator is divisible by the denominator, then you can take, let's say, an integer number of times, you can take the denominator out of the numerator. That is what they are telling, right? And what we have to prove is that that integer number of times is a perfect square. That's what we need to prove. But just as a starting point, let us try to take out this numerator denominator from the numerator. That should be the easy approach, right? You have b here. Let's say I split it as b minus a. The top part is b minus a. The bottom part is a. I mean, the total is b. I just split it as b minus a and a, right? But this is the same square as you see bottom, right? AB, AB. This is the same area. So these many people, see, I'm just cancelling out. And this one, I'm cancelling out with this one, right? So what is remaining in the top? What will be remaining? A square with 1 lagging. A square, let's say A square with this part taken away. This is lagging. That will be remaining. What else will be remaining? You will have a B, B minus A, right? This is what will be remaining. Now again I take off this thing from this. What is remaining, I again take it out. What will happen? This one I'll take it out from here. And what will this be? B minus 2A. The same concept. I'll again take out another A. So B minus 2A. Right? Like that, if I take out, let's say, 8 times, what will happen? This square. I mean, I take out A square times. Sorry. I take out A square times. What will happen? This entire square will be finished by this 1. Right? And AB will keep on getting what you tell. A square times I'm coming, taking out. So what will remain? The remaining square will be, uh, I'll show it. It will be basically a rectangle with B, and here it will be B minus, this is A square times A. So it will be A cube, right? This will what will be, that is actually remaining. Okay. Okay. So let me keep that what is remaining. I'll keep it here. I'll keep it as B minus A cube, right? This is what is remaining. Now, let it stay there. Now, we'll think about another concept. I'll just tell. Let's suppose you have 3 plus 3 plus 3 by 3 equal to 3. Okay, just think of this. Think of this something like this, right? So you have a numerator. Suppose this here, you know this, there are 3 threes and you're going to, let's say, uh, take out a 3, right? Suppose you have a black box. These things, what is inside it is not clear. You have a black box 1 and you have a black box 2. Okay, and you have a denominator, let's say D. You have a D, right? So if I'm asking to actually divide, what will you do? Divide this. If I'm telling that this two black boxes perfectly, perfectly divides. I mean, D can perfectly divide the two black boxes, or is divisible by D. These two black boxes are divisible. Some of these two black boxes are divisible by D. What thing I can actually do is this D. I will let's say I split D into, let's say, M1. Let's say I take A1 out of this black box and I take A2 out of this black box such that D equal to A1 plus A2. Okay. I'm splitting this D, and a part of this D I'm taking out of this black box and a part of this D I'm taking out of this black box. Right? I'm doing that M times. Right? M times A1 plus M times A2. Right? Now, after some time, after M times, what happens is this black box is exhausted. It doesn't have any members in it. Now, if still the numerator has to be divisible by the denominator, what should happen? The next n times, basically, I have to take a1 plus a2, pardon me, out of this black box 1 alone, right? Only then the total will be divisible by, total numerator will be divisible by the denominator, right? So you get the idea, right? So only then the total. So here, suppose, so this idea, having described this idea here, now we'll go back to this, what is remaining, right? So now obviously a square times, this is the portion that is remaining when you have taken, let's say, a square plus b square. Out of a square plus b square, you have taken ab plus 1 a square times, right? You have taken it a square times, you have actually taken ab plus 1 out of this, and this is what is remaining, right? If this is 0, then you have your solution, that if this, suppose this is 0, then you know that okay, a square is my what you tell quotient, and that is a perfect square. Problem solved, right? But when you solve this, you need to think of two things. It's a big subset and you have a small subset. So you know that now if you keep the coefficient as a square times, right? See, first of all, a and b are, what you tell, I haven't assumed anything about a and b, right? Only assumption is b is greater than a. That is my only assumption. But if suppose whoever is the greatest integer, I called him as b, right? So then that is not also perfect. That's not actually an assumption also, right? Right. So even so in that manner, so I'm telling that if a square is actually a perfect square, that suppose let's say a square plus b square by ab plus 1. See, all the things, all the coefficient, what you tell, quotients that can actually divide, let's say a plus b divides, let's say a square plus b square n times, right? Of all the n, you know that if it is a square is a part of a square will actually divide it, right? But our proof is actually the reverse. Now we need to prove that a square is the only thing that will be in n. We need to show that this area is 0. This nothing will, only a square will actually divide, right? The remaining part is 0. That is what our proof has to be centered around, right? Now let us see what is the remaining portion, right? Now having that idea in my mind, now, and the black box idea, now you know that this is what is remaining. Now black box 1, that was earlier you had an a square, right? Now that a square is exhausted, black box 2 is exhausted. Now everything has to come out of this black box 1, right? Right? Now let us see what will be this area. This area will be b into b minus a cube by ab plus 1, right? Now, if we can prove that this is not, that b into b minus a cube is not what you tell divisible by a plus 1, ab plus 1, then the remaining portion can never be divisible by a plus 1, a plus 1. Then the only solution is a square, right? If this is only 0, if this has to be 0, that is the only way that a square plus b square can be divided by ab plus 1, right? Right? Now that comes out, right? If you can tell that ab plus 1 cannot divide what you tell this area ever into a proper integer, right? If we can prove that, then our overall proof comes out that only solution, if it divides, the only solution is a square, which is a perfect square. Now our only job is, now we have translated our entire problem to the only thing that this thing should not be a proper, what you tell, integer, should not be a proper integer. If we can prove that, we are done with our proof, right? See, this is okay. So where we stopped was in proving that b into let's say b minus a cube by ab plus 1 is never an integer, correct? That is where we actually stopped. So uh, now I'll introduce a different idea here. Suppose you have something, let's say some quantity q, right? And you want to divide it by w plus r, right? So like how many w plus r are there in q is what you want to know, right? Now, what would happen if, let's say, w by r perfectly divides q? Okay. Now, what if I tell you that, let's say, instead of that, wherever you see w here in q, right? Q is split as w plus, let's say, something else, w plus p. You're able to find the w in what is there? You're able to see the w in p, right? If you just think now, w plus r is what you need to actually take out, right? W is already taken out, right? Now, if you substitute this, let's say, this w with minus r, what will happen, right? Instead of, you are just taking away w, right? But you should have actually taken away w plus r. So you are actually substituting w with minus r, right? In q, if you substitute, where if you are able to write q as a function of w, and you are able to wherever you see w, you are able to write minus r, then minus r q of let's say you are able to write it as w, and you're writing q of minus r, you're substituting w to be minus r, then that should be also divisible by w plus r. I think am I going bit till bit fast, I think. So what the idea is, you have less 3 plus 3 plus 3. Hmm. And you have, let's say, 2 plus 1. You're going to divide it by 2 plus 1. So instead of always what you tell dividing by 3, you take out 3 threes out of here. Instead of that, let's say you have these 3 threes, you're writing as 2 plus 1 plus 2 plus 1 plus 2 plus 1. Somehow you are able to get this 2 out, right? Now in place of 2, if you put minus 1, what will happen, right? Minus 1 plus 1, minus 1 plus 1, minus 1 plus 1. So I mean, that will also amount to be 0 actually. When you take out this minus 1 out of these, that will also amount to be 0. Just like you're taking away 3 threes out of this and making it 0. Now if you take out minus 1, right? That is, you're actually split. It's wherever you see 2, you're actually putting a minus 1 and you're taking it out. Then also this thing will actually divide. That is the idea that we're going to use here, right? So b into b minus a cube by ab plus 1, right? So now I'm going to use the same idea here. I'm going to write it as b square minus b a cube by ab plus 1, right? So I'm going to write as b square minus ab into a square, right, by ab plus 1. So this is actually a modular arithmetic method, right? But the idea is very simple. You substitute whenever you see ab, you substitute minus 1. So it becomes b square plus a square, and now you need to divide by ab only, right? Right? Now you needn't actually what you tell. Now you can just take out this ab alone. That is the idea. So this, is it possible? If you are able to prove this, it is equivalent to proving this is divisible by this is the same thing as proving this one, right? So that is the idea. So now a square plus b square, now if you write it, it is like b by a plus a by b. This can never be an integer because, see, let's say you have any number 1 or 1, 3, right? If this becomes greater than 1, this should be less than 1, right? This is always a fraction. This is always an integer, right? Integer plus fraction will always be a fraction. Correct? That is the idea here. So this will always be a, this will never be an integer, this will be a fraction. So that is why this one will always be a fraction. This one can never be a, what you tell, an integer. So in that way we have actually proved that this can never be an integer. So in that manner, from whatever we saw now, we have a square, that is the only way. The remainder b minus a cube, a square times a and b by ab plus 1, right? Plus 1. See, you have to take out a square times. There is no other way to make this, what you tell, divisible by ab plus 1. It has to be a square, which is a perfect square. Thus, we have actually proved our identity, right? So this was a good question. Thank you for sharing your time.